Welcome back, game theorists. Today we are still in chapter 16, looking at auctions. We established in the previous episode that there is no pure strategy Nash equilibrium to an all-pay auction. So instead, we're going to look for a mixed strategy Nash equilibrium. So players will randomize. So to set that up, we first need to review some basic stats. You might have seen this already, taking a college level stats course, or it might be new to you. So I'll define P of B is the cumulative distribution function. And I'll tell you what that means in just a bit. It's often abbreviated as CDF in a lot of the economics textbooks and articles. So that's the probability that someone bids less than B. So here are some examples as to what that might mean. So let's say you have some P of B and you get this value of P of, let's say, 0.75 is 0.2. That means the probability you bid less than 0.75 is going to be 0.2. I'll use prob here for probability. Here's another example. Let's say that P of 0.4 is 0.1. That means there's a probability of 0.1, 10%, that you bid below 0.4. I'll do one more easy example before I look at more sophisticated cases. Maybe P of 2 is 0.35. So there's a 35% chance that you bid less than 2. All right, so those are some very basic examples. I'll show you some graphical examples as well, so you get a clear grasp on what is going on here. Here's a very easy one. P of x is just x. So graph x over here, and I'll put P of x over there. So if x is 0, then P of x is 0. That means there's a 0% chance of bidding less than 0. You never make a negative bid. Well, that makes sense. Usually can't make negative bids. And x is just a straight line. And that's going to stop here at 1 because probabilities cannot exceed 1. So what that tells you is that the probability of bidding less than 1 is 1. Or probability of bidding less than, let's say, a third, put 1/3 over here. Well, it's going to be 1/3. So you can see it's a very, very basic example. So why is this a very basic example? It's to show you there's also a very closely related concept. We said this was the cumulative distribution function, often abbreviated as CDF. The related concept out there is the PDF, which is called the probability density function. So this PDF, this probability density function, is always the derivative of the cumulative distribution function. So you use it much the same way, though the interpretation of the graph is a bit different. So in our earlier example, we had p of x being just x, and now it's the cumulative distribution function, the CDF. If you take the derivative, well, derivative of x is just 1. And now you have the PDF, the probability density function. So you can draw a graph. It's a very basic graph. It's a very easy example. So just a line at 1. And I know that probabilities can't, I know I was going to stop over here at 1 because you had the graph back there. Stop at 1. My graph is not to scale. Pretend I drew that better. Pretend I drew a square instead of a rectangle. So how to interpret this graph? Well, if you want to know the probability of bidding less than 1/3, with this graph, that corresponds to all the area between 0 and 1/3. And you can see that two stories match up here. So in this case, our rectangle is a height of 1 and base of 1/3. So area is going to be 1/3. And that's exactly what we got back here, where we had this graph. We said probably bidding less than 1/3 was equal to 1/3. So you get the same answer with two different approaches. You could take your CDF and just plug in. Alternatively, you could look at your PDF and find the area under it. That was a very, very basic example, or a trivial example. Let me show you one more case that's a bit more sophisticated, and then we can go back to looking at all-pay auctions. So I had things just be linear. P of x is x. Let's try something else. Let's take P of x being x squared. And that's going to be our cumulative distribution function. So let's see. We start at 0 because 0 squared is 0. And we know it has this kind of a shape. And we also know probabilities can never exceed 1, so this had better stop up here at 1. We know that x squared equals 1 when x is 1, so that's how you can pin down this value. So what's the probability of bidding less than 1/2? So just plug into our function, p of half. So that's going to be a half squared and that's 1/4. So now I get the same result again using the PDF instead of the CDF. So we said the PDF is a derivative of the CDF. So derivative of x squared with respect to x will be 2x so that means our intercept is 0 and it means that our slope is going to be 2. So what are the bounds on our shape here? Well, I know that total probability can't be more than 1. And I know that with a PDF, the probability is the area under it. So the area of this triangle in total cannot exceed 1. So a triangle with base 1 and height 2, then this whole area would be half of 2 times 1, which will be 1, so that works out. Total probability is 1. Or you can just go back to your CDF. We said with our CDF, x can't exceed 1, so that implies the same x can't exceed 1 over here. Now notice over here, PDF, this is not a mistake. You can have values bigger than 1 over here. That's because of the CDF, this value is not the probability anymore. Rather, the PDF, the probability is the area under it. So this number can be bigger than 1 as long as the area under it is less than 1. So this is not a mistake. So I said we can verify that you get the same answer with this different approach. So what's the probability of a bid below 1/2? Well, because we have a PDF here, not a CDF, what you got to do is look at the area under it. So 1/2 is going to be over here. So we're trying to find this area. So I know the base of my triangle. What's my height? Well, it's given by 2x. So if that's 1/2, this had better be 1. So base times height divided by 2, that comes out to 1/4 again. So 1/2 of 1/2 is 1/4. So again, you get the same answer either way. So the PDF and CDF give you different tools to get the same results. All right, so that's our very brief intro to stats. Now let's apply it to all pay auctions. So P of B is going to be the probability of bidding less than B. So that's our CDF. More precisely, I should say, it's the probability that one person bids below B. So what's the probability of two people bidding below B? So you have to have this happen, and then you have to have it happen again. So P of B squared is going to be that probability. So might have to think about a more concrete example. So let's say that it's a probability of half, 50%, that someone bids below B, that one person bids below B. So one person bids below B with probability 1/2. What's the probability of two people bidding below B? That's going to be half times a half. So half squared, it's a quarter. A quarter. So how likely is it that instead you have three people bidding below B? Well, that's going to be P of B cubed. So I pick up my example. There's a probability of half of people bid below B. Then probably again, three people bidding below B is going to be half times a half times another half. That's a half cubed, or 1/8. So you can see a pattern here. To get two people bid less than B, it's got to be P of B squared. To get three people bid less than B, it's got to be P of B cubed. So P of B to n minus 1 is going to be probability that n minus 1 people bid less than B. So what's so special about n minus 1? There are n people at this auction. You're one of them. So if you bid B and everybody else, all n minus 1 of them, everybody else bids less than B, what happens? Well, you have the highest bid in that case. This is the probability that you win. The probability that you outbid everyone else. So that's the significance of this thing we showed over here. So now I know what's the probability that you win. So if you win with, say, probability 40%, that means you lose the other 60% of the time. So 1 minus that is going to be probability of losing. So there is a possibility of a tie, but if we're picking numbers that are continuous, then the probability of tie is going to be exactly 0. Or should be 0. I shouldn't quite say exactly, it's going to be negligible. I should say more precisely. So now I'm going to set up the expected payoff. So we said if you win the auction, you get V minus B. You get the object, which you value at V, and you pay your bid B. So this is what you get overall. Because in all pay auction, you pay your bid even if you lose. So like I was saying earlier, the team that loses the big game does not get a refund all the hours they spent training. So that effort is their bid. We just established that the probability of winning is P of B to the n minus 1. And the probability of losing is 1 minus that. So now we have tools in place to set up the expected payoff. So if you win, you get V minus B. The probability of winning we established was P of B raised to the power of n minus 1. If you lose, you get minus B. The probability you lose is, we established, 1 minus P of B to the power of n minus 1. So before you go forward, it's helpful to simplify a bit. So I'm going to just expand the terms in these parentheses. So that's this one expanded. So minus b times 1 be just minus b. Then minus b times a minus, so 2 minus to give me a plus. So I have plus b times p of b to the power of n minus 1. Well, that's convenient because these guys cancel out. So I'm left with e pi expected payoff v times p of b n minus 1 minus b. There's some intuition behind this thing we have so far. So you could view it as I'm paying b no matter what. So I'm paying b with probability 1. So I pay b win or lose. It's an all-pay auction. I collect v, the value of the object, with this probability of winning. So it's probability of winning times v minus the bid I pay no matter what. So to maximize that expected payoff, well, let me tell you what your book does. So your book notes that you can always get yourself a payoff of 0 by bidding 0, something we established back in the previous episode. So your book cites the opponent's indifference property that says for a randomization, you have to be indifferent between each of the pure strategies involved in the randomization. I'm not quite sure that really applies here logically. So the book's answer turns out to be right in the end, but the logic used to get there might be a little bit shaky. Here's why I say that. I'll put a question mark here because I'm not really sure if this is really valid logic. Though by coincidence, the answer is right. We also know from Chapter 7 that sometimes players don't use all of their available strategies in their randomization. So they are indifferent between the strategies that they do use. That part's right. We haven't established, though, that you're going to use 0 in your randomization. Without that extra step, I don't think we can logically really appeal to this. But again, by coincidence, this method does give you the right answer, and it's easier than the proper method, so I'll show you that. Here's another part I think is kind of shaky in the reasoning. So it's with the opposite difference property, it'll be there to each of your pure strategies. But this is not comparing two pure strategies, comparing one pure strategy, bid 0 all the time, with something that's not a pure strategy. We compare the mixed randomization. So logic's a little bit shaky here, though the result is correct. So what you get is you gotta have this expected payoff be equal to 0, and now we can solve for P of B. So first I'll add B to both sides. So I get that. And now to try to isolate the P of B, I'll divide both sides by V. The last step to isolate, or perhaps I should say in these times, to quarantine the P over B, we had to raise both sides to the power 1 over n minus 1. So that will be the cumulative distribution function that everyone uses in the mixed strategy Nash equilibrium. So I said the logic here is a little bit questionable, and I said why that was. Let me show you what the procedure would be to get the answer that does not rely upon this shaky logic. So we already had that expected payoff is V of P times B to the n minus 1 minus B. We showed that back over here. So I'm just copying that down. Well, you know what happens when you have an expected payoff, right? We maximize it. We maximize that by taking a derivative and setting that equal to 0. So the variable we choose is b. Take the partial derivative with respect to b, because b is our bid, and we choose what our bid is. So be a little bit careful here. First step, we got to apply our power rule. So the exponent, n minus 1, comes out in front. And then you reduce the exponent by 1. It's just like when you have, say, y equals x cubed. You take your derivative, then you get 3x squared. So that exponent comes out in front, and the exponent goes down by 1. So same thing here. The n minus 1 comes out in front, just like the 3 did back there. And the exponent goes down by 1, so we're from 3 to 2 in our example. Now it goes from n minus 1 to n minus 2. Careful! Let's not forget our friend, the chain rule. So you have a function within a function. So you have a function raised to an exponent. We deal with the exponent first. Now, chain rule says you got to multiply by the derivative of what's inside. That's p prime of b. So don't forget your chain rule. Very last part, derivative of b with respect to b is just 1. As usual, set your derivative equal to 0 to maximize. So what you get here is a rather messy differential equation. So you got a derivative, you have an exponent here, and the same function. So there are ways to solve this. It turns out that this p of b we got over here via a dubious method happens to work. So that's why I said your book's approach, while the logic is shaky, it gives you the right answer. I won't show you how to solve this equation here because this is not a differential equations class, but you could verify that this works. So that's how you solve all pay auctions when everybody has the same value. Be sure to join us for our next episode, which we explore what happens if people have different values.